So our next family of lipids is something called triacylglycerols. And we should be able to look at this name and go back and kind of review some of the things that we talked about last semester in Organic Chemistry 2 when it concerns the carbonyl family and be able to pick out the large majority of what triacylglycerols look like as far as structure goes. So let's see kind of what this has in store for us. If I wanted you to break down this name, the very first thing that we would do here in the beginning is look at this word tri, and hopefully, you would be able to tell me that tri basically means three, triangle, right? This is not a new prefix that we have just been introduced to, so three is representative of tri. So we've got three of something, well, we've got to figure out what that is. We then go to the next part of the term, and that's this thing called acyl. And acyl we have saw before in the past as well, and this was in our Organic Chemistry 2 course, and the acyl group was another term that was used to describe a C double bond O at that time. So when we talked about the acyl group being attached to something, we were looking at the C double bond O group as a whole. So we've got three, maybe C double bond O groups on this molecule. And now we get to kind of the new piece of the word, and this is glycerol. Now I want to take a look at the OL, and glycerol is OL ending, basically is an alcohol group, and OL is OH. So we know that maybe glycer, whatever the term glycer is, probably has an OH group on it. So we're going to have to determine really what the new piece of this word is, and that is the term of glycer. And glycer is something that you're going to have to memorize because it really is the backbone to all of the triacylglycerols that we are going to talk about in this video and maybe even in the next video. So let's take a look at the structure for glycerol. So glycerol is a 3-carbon backbone, carbon, carbon, and carbon. And if I just want to concern glycerol, and that is it is a 3-carbon chain, each with an OH group that is on it. So this is what we call glycerol. It is a very important structure that we should memorize, not only in lipids, but basically in organic chemistry as well, because we tend to run across glycerol quite often. And it's very important for me to understand what glycerol is and what it's all about. So if I look at glycerol, I see a 3-carbon chain, each with OH groups. There's something that I can already take away from the picture. Number one, it has OH groups, and that basically means it can participate in hydrogen bonding, and not only that, but this is limited as far as the organic structure goes. So what I'm basically trying to get across is that we've got quite a bit of polarity on this molecule, and we have quite a bit of hydrogen bonding on the molecule, and we have very limited organic key parts of the molecule. And because of that, glycerol has very viscous, it's very thick. So if you go to the lab and you take a look at glycerol and you pour it out into a beaker, it will be very oily in nature. Sometimes instead of glycerol, we use the term glycerin, and very often we're referring to the same thing when we do that. So glycerol and glycerin is kind of used interchangeably. It's 3 carbons, each with an OH group on them. Now, this one, of course, has 2 hydrogens up at the top to give me 4 bonds. This one only needs 1 to give me 4 bonds, and this one needs 2 to give me a total of 4 bonds. So there is our glycerol portion of this molecule. Now, to make a triacylglycerol, I need to add something to glycerol, and what I need to add to glycerol, it's a fatty acid, and this is something that we've already spoke about as well. So we can go back and take a review of what these fatty acids are, and we look at the functional groups on them, and we see that they have random alkyl groups. They can be anything that they want to be, so I'm just going to call them random alkyl group 1, random alkyl group 2, and random alkyl group 3. For fatty acids, we also know that this has to have a C double bond O group. So I'm going to see a C double bond O group that's here, and then off of this C double bond O group, we have an OH, because by definition they are acids, so they are proton donors. So I can bring into the picture 3 fatty acids. And when I do this and I mix these two things together, a reaction can take place. And what we see happen here is that my glycerol will react with my fatty acid, and what I end up with is a C double bond OO and then some kind of random alkyl group that it wants to bring into the picture. And I get these ester groups that begin to be formed. So this now is kind of a fatty acid slash ester. And this is something that I'm going to talk about in much more detail a little bit later on. The problem, though, is that people get confused here. Let's take a look at the chemistry of how these two things mix together. This is an acid. All of these are acids, right? So by definition, this carboxylic acid, because that's what it is, this is a proton donor. And when this donates a proton to solution, it can easily protonate the OH groups on glycerol. And if this becomes protonated, we've already seen that that makes the alcohol group a very good leaving group. This is something that we talked about last semester in our previous course. So we see the removal of the OH group, and it disappears on me. And this opens up a site of attachment for this carbon, and this is going to have an incoming group that's going to attach and substitute itself for the OH group. And that piece is the OC double bond O and the R group that it brings into the picture. So that means that this oxygen, this carbon, this oxygen, and these alkyl groups are coming from the fatty acid parts of this whole dynamic of reacting glycerol with a fatty acid. And then when that happens, this is what we call a triacyl glycerol. Triacyl, so there's 3 of the carbonyls that are there, and glycerol basically meaning it's coming from a glycerol backbone. At least that's what it was before the OH groups got substituted for the ester groups that I have just now drawn. So every one of these is coming from the fatty acids. So I see my O, my C, my double bond O, and my R groups that are tagging along. All right, so general terminology as far as it's concerned, triacylglycerols typically get shortened. We leave off the term acyl and we call this a triglycerol. So triglycerols are very often, this is something especially if you're concerned about your health, if you're concerned about heart disease, if you're concerned about heart attacks, whatever the case is, you're looking at triglycerol. Triglycerol is something very important when it comes to blood chemistry and when it comes to clinical chemistry, and we'll expand more on triglycerol here in a minute. But this is our triglycerols, our triacylglycerol functional groups. So glycerol backbone, 3 carbons, right? And then each one of these has an ester group on it that brings to the picture a random R group. Now, there's 2 different types of triglycerols. One is going to be labeled as a fat, and one is going to be labeled as an oil. This is something that we've mentioned before in the past, and I'm going to beat a dead horse all over again. So fats, of course, are solids at room temperature. Oils, of course, are liquids at room temperature. Fats are things like butter and lard. Oil is something like vegetable oil, olive oil, canola oil, almond oil. You get the picture. So we can assign these things with melting points, and as far as melting points go, well, fats have very high melting points. So once again, I'm going to come down here to the side and I'm going to put 25 degrees as room temp. So if something is higher than 25 degrees as far as boiling point or melting point goes, let me do melting point here because we're talking about lipids, which are fats and oils, so let me do melting point. If something has a melting point higher than 25, what that means to you is that once you bring it into the room, it is still a solid at room temperature. And if this has maybe a melting point of 40, what that basically means is that you're going to have to heat that substance up till 40 degrees before it melts. So at room temperature, it is a solid. So fats have high melting points. And when we say high, we are talking about traditionally anything higher than 25 degrees. Now there's a gray area in there. It can be much higher than 25. So 25 degrees could still be a liquid, 26 degrees could still be a liquid, but theoretically, room temperature at 25 degrees, well, that's kind of the dividing line. If you want to be black and white, that's going to be our black and white area. Liquids, on the other hand, have very low melting points, and these are traditionally lower than 25 degrees Celsius. So if I have something that has a melting point of 20, I bring it into the room, well, the thing is already melted on me because my room temperature is 25. So if the melting point's at 20, it's already melted. So it is a liquid by definition. Not only that, but something else that we can bring into the picture here is fat typically comes from animal sources, and oils typically come from plant sources. So this is going to be a test question. This will also be probably a question in mastering chemistry. Describe some differences between fats and oils, and this is something that you can do. So fats are solids, and they have very high melting points, and they traditionally come from animal sources. And oils are traditionally liquids. They have very low melting points, and they traditionally come from plant-based sources. So this is something that we can take to the bank. We'll see it again. We'll see it on a test. It is a very common question that appears over and over and over, and this is giving us an insight of triacylglycerols. So, with that said, let's stop the video here. We'll continue the discussion of triglycerols in the next video, and we'll expand this horizon a little bit more.